Hi everybody, this video is on section 10.2. It's going to be the existence of the Laplace transform. And the inverse transform. Okay, so question. What we are interested in here is what types of functions have a Laplace transform. Well, remember, if f is piecewise continuous, certainly if f is piecewise continuous on 0 to infinity, that means that it never gets very large anywhere we go, which means that this integral always exists, right? The question is, does this exist as b goes to infinity, right? So when does this guy exist? This is what we're asking. What types of functions does this exist for? So I would like for us to learn a particular vocabulary term here. A function f is said to be of exponential order if there exists m and alpha constants such that f of t is less than or equal to me to the alpha t for all t bigger than 0. Okay, essentially what we're saying is that the function is bounded above by an exponential function. This is what it means for it to have exponential order. Okay, so example, f of t is equal to 10 e to the 7t cosine of 5t, right? This function here is of exponential order since the absolute value of f of t, right, if you actually take this absolute value, this is going to be less than or equal to, since cosine of 5t is less than or equal to 1, this is less than or equal to 10 e to the 7t. So we could see that this is clearly of exponential order because m takes the place of 10 and your alpha would be 7, right? Okay. So what's our notation? Let's let e, the way that we write this, e of 0 to infinity, this is going to be a set, and this is the set of all piecewise continuous functions of exponential order. Okay. Turns out that e of 0 to infinity is a vector space. What does this mean? It means that if you add two functions of exponential order, you get a function of exponential order, and it satisfies all of the axioms, okay? So, theorem. Why do we care about functions of exponential order? Well, if f is a function of exponential order, then there exists an alpha that's a real number such that the Laplace of f exists for all s bigger than alpha. Okay? So what we're saying, this is an important theorem, okay? This is saying that the Laplace always exists for all functions that are of exponential order. Note, the converse is false. In other words, just because the Laplace transform exists, it doesn't mean that a function is of exponential order, okay? So you got to be careful. It only goes one way. So let's let V be the set of all functions of exponential order such that they're actually continuous. Not piecewise continuous, but they're continuous. And if we look at L, the Laplace transform, as a map, right, it takes V to some set of functions, right? So let's go ahead and restrict it to the range of this guy. So it turns out that this map is 1-to-1. Okay? So this map is 1-to-1, and also, I'll say and onto. What does this mean? This means, as we learned earlier in the class, that the inverse of this transformation exists. So this leads us to a definition. The linear transformation, we write it like this, L inverse, and it maps that. And how do you define it? So what does it mean to take the Laplace inverse of capital F and for it to equal little f? This means that the Laplace transform of little f is equal to capital F. Okay, so this is what the Laplace inverse does. It brings us the other way. So note, L inverse is called the inverse Laplace transform. Okay? This is really important. We're actually going to be using the inverse Laplace much more than the Laplace transform once you see where we actually go with this, when we start solving differential equations. Okay, so let's do some examples. Recall that the Laplace transform of t to the n is n factorial over s to the n plus 1. So this leads us to the following formula. What's the Laplace inverse of 1 over s to the n plus 1? Well, if I divide both sides by n factorial, I get exactly t to the n over n factorial. So this is 1 useful formula for the Laplace inverse. Every formula we had before can reverse, right? So remember, we also did the Laplace of e to the at, and remember we got 1 over s minus a. What this means is that the Laplace inverse of 1 over s minus a is equal to e to the at. Okay? We have some more. Also, if we reverse the sine and cosine formulas, here's what we get. The Laplace inverse of s over s squared plus b squared. This is equal to cosine of bt. And the Laplace inverse of b over s squared plus b squared. This is equal to sine of bt. And again, all of these are just the Laplace formulas, but in reverse, okay? Okay. So, note, linearity. Since linearity holds for L, it's got to hold for L inverse, right? These are linear transformations. Okay, so let's use this fact that linearity holds for the Laplace inverse to calculate the following, okay? So let's do an example. Let's find the Laplace inverse of capital F of t if, first, capital F of s is equal to 2 over s squared. Okay, so let's try this. What would be the Laplace inverse of 2 over s squared? Well, we know we can pull the 2 out, right? So this ends up being 2 times the Laplace inverse of 1 over s squared. So s squared, you can think of it as s to the 1 plus 1. So we are going to use the formula from before, but with 1 as our n. So it ends up being 2t to the 1 over 1 factorial. So that's just 2t. So the Laplace inverse of 2 over s squared is equal to 2t. Let's try another example. So this will be part B. Let's suppose that capital F of s is equal to 3s over s squared plus 4. Okay. Well, the Laplace inverse of 3s over s squared plus 4, if you pull the 3 out, it becomes the Laplace inverse of s over s squared plus. Now I'm going to write it in this form. Instead of writing s squared plus 4, how about I write it as s squared plus 2 squared? If we look at the sine and cosine formulas, we realize that this is just the formula for cosine, but with the b equal to 2. So this is just going to become 3 cosine of 2t. Let's do a more interesting one. And by the way, this is a preview of what's to come, because you're going to have to do something like this all the time when you're actually solving these differential equations. Okay, let's say you're asked to do the Laplace inverse of this. Unfortunately, there is no nice way of doing this. However, we can use partial fractions because we would like to try to write this as. So using partial fraction decomposition, we know that this is equal to sum a over s minus 1 plus sum b over s minus 2. So let's use partial fractions to try to figure out what we get, right? So we end up with 3s plus 2 is equal to a times s minus 2 plus b times s minus 1. And if I plug in s equals 2, I end up with 8 equals b. And if I plug in s equals 1, I end up with 5 equals negative a, or a equals negative 5. So what does this mean? This means that I'm really doing the Laplace inverse of negative 5 over s minus 1 plus 8 over s minus 2. So again, I'm going to distribute the Laplace inverse to each of these, and I know I can pull the constant out. And what's the Laplace inverse of 1 over s minus 1? Well, we actually learned that that's just going to be e to the t, right? So this is going to be negative 5 e to the t, and then it's going to be plus 8 e to the 2t. Okay. Again, we're using the formula that, if we come back to the previous page, right, we're basically just using this formula right here. Okay, we use this formula for different a's in this last problem. Okay, so just showing you what occurs when you actually find these things. You're going to need to split these guys up, sometimes using partial fractions, so that we can get some pieces that we recognize. Okay. All right, just as an aside here, you may be wondering, what about for functions that are not continuous? What about piecewise? So if functions in V are piecewise continuous, instead of continuous, L is not 1-to-1. Okay, what this means is that L inverse is not unique. Okay? However, something worth noting is that solutions to IVPs won't be affected. In other words, it won't affect the actual solution of the initial value problem. And this is because the inverse Laplace transforms will only differ at their points of discontinuity, so it's not going to affect the value that we get for an actual initial value problem. All right, guys, so that is it for 10.2. Short section is just laying down some theoretical groundwork and introducing you to the inverse Laplace transform. Thank you so much for watching.